Okay, so after you watch this video or otherwise, let's look at what graphs are. I guess you also may know them from whatever that course that you took before, TNSL 24, I think. Again, we are calling it pre-BLA because you learn in MATLAB and other things that you will also use here in the BLA course in TNSL 20. But just for you to refresh your memory, or if you see it for the first time, then, well, here it is. A graph is this object which is defined by vertices and edges, and every edge connects two vertices. And if the edge connects vertices u and v, edge E connects vertices u and v, then we will denote it like this. E is equal to uv, or sometimes we may use this notation. Again, E connects u to v. One important notion in the graphs is that the graphs can be directed, like for instance this graph in the example. Here every edge has a tail and a head. It goes from one vertex to another, but kind of not in the other way. It models, one-way roads. And in paths and in flows, which will be the first two problems that we are considering in this course, we will be working with directed graphs. In almost all other problems, we will be talking about undirected graphs, with the exception of, well, again, longest paths on directed acyclic graphs. But again, I will make a special note that we are working with directed graphs. So it's important to understand whether you have a directed or undirected graph. In particular, for now, we will be working with directed graphs. And for directed graphs, the vertices are often called nodes, and the edges are often called arcs. It's not wrong to call a node of a directed graph a vertex, or an arc of a directed graph an edge, but sometimes if you really want to make the distinction or understand the distinction, if somebody means it, then vertices and edges mostly refer to undirected graphs. Nodes and arcs mostly refer to directed graphs. Okay, so graphs, or at least small graphs, can be depicted. Well, here is a picture of a graph, and this thing down here, maybe I should use a notation. So this is not a kind of graph that we will be talking about in this course. No, we will be talking about graphs like this. So how can you specify the graph? Well, you can just give the edge list. Again, this is something that you hopefully worked on, or at least touched upon in the pre-BLA course. Well, we just list the edges. One edge connects node 1 to node 2, another edge connects node 1 to node 3, node 1 to node 4, and you specify all the connections: 2 to 5, no, sorry, that was 2 to 6, 2 to 5, 2 to 6, and so on. So, and again, with this convention that we can use this notation for edges or this notation for edges, this edge list is just as good as this edge list. So you just list in the edges. Another way to specify a graph is to use the so-called adjacency matrix. So if the graph has n nodes, then the adjacency matrix is n by n matrix. Like for instance, this graph has 6 nodes. So this matrix will have 6 columns and 6 rows. And the adjacency matrix will have a 1 in ith row and jth column if there exists an edge from I to j. Okay, like for instance, well, we have an edge from 1 to 2. So in row 1 and column 2, right here, we have a 1. Similarly, we have an edge from 1 to 3. So in row 1 and column 3, we have a 1, and so on. Node 1 is connected to node 4. Node 2 is connected to nodes 5 and 6. Here is node 2. Here are the connections to 5 and 6. And it's not connected to any other vertices, so all these entries are zeros. And so on. So node 3 is connected only to vertex 6. Here you are. Node 4 only to vertex 6, node 5 only to vertex 6, and node 6 is not connected to any node. So there are several nodes that connect to vertex 6, and therefore there are several ones in the 6th column, but node 6 itself is not connected to any node. There are no edges that come out of node 6. There are no edges for which node 6 would be the tail. So therefore the row of node 6 is full of zeros. Okay, so that's the adjacency matrix. It has as many rows and as many columns as there are nodes in the graph. And the entry is 1 when there is an edge going from node I to node J in the row I and column J. Okay, any questions about the adjacency matrix? We will have more examples. I mean, I will draw an example on the Jamboard, and then we'll create the edge list and the adjacency matrix. And also in your homework, you will be asked to create graphs, create adjacency matrices and edge lists for them, and so on. So that's how the graphs are represented in a computer. I mean, the computer cannot look at a picture like this. Computer needs to have the list of edges, or to have the matrix represented the graph, the adjacency matrix. That's how computers work with graphs. So the graphs may have weights on edges, and if they do, then they're called weighted graphs. So in the weighted graphs, we have the vertices, the edges, or nodes and arcs, and also weights. And a weight is an assignment of numbers to the edges. So W of the edge UV is the weight of this edge. So these weights may represent different things, like in shortest path, they represent lengths. So sometimes we say that they are lengths of the edges. Sometimes we say that they are costs of the edges. They may represent various things, but well, the different edges may have different weights. And we can use notation like this for the weight of the edge, or sometimes I would use notation like this. So this is the length of the edge, you know, like the length of a segment AB. Like right in geometry, if you have 2 points, A and B, then, well, the length of the segment is AB. So I'm borrowing the notation from there and using this to represent the length or the weight of the edge UV. Okay, and here again on this graph, now there are some assignments of weights to the edges, and our convention is that if an edge has no label, then its weight is 1. Like this edge has weight 1 and this edge has weight 1, but I'm not explicitly mentioning it. If they are unlabeled, then they have weight 1. So here is the assignment of the lengths to the edges of this graph. The edge 1, 2 has weight 10, and so on. Edge 4, 6 has weight 1. Here it is because it's unlabeled, and so on. Okay. So these are the weighted graphs, and in fact, for the shortest path, it will make a lot of sense to use weighted graphs, because the weights of the edges will represent, you know, the length of the road, or the time to travel along the road, or another cost to travel along the road, and a fuel cost, whatever you're trying to minimize. Okay, and before we go into the algorithm for finding shortest paths on the graph, let's just have an example of graphs and their adjacency matrices and other things. So I'm again switching to sharing my other screen, on which I have the lectures and the Jamboard. So I will also over here open up the slides for the graphs and their adjacency matrices. And here in Jamboard, I'm now on page 2. So you hopefully see page 2 in your Zoom, but also if you're following the Jamboard, otherwise you would have to change the page. There are these arrows, and you can go between pages. Here's the page with Euclid's algorithm. Here's the next page. So if you're not following Zoom, but sitting in Jamboard, which is fine, then you have to be on page 2. And well, we'll just come up with some graph, start drawing the graph more or less arbitrarily. Maybe it will have, I don't know, 4 nodes, and I will draw some connections. So here is our graph, and well, let's do the adjacency matrix for this graph. The adjacency matrix will have 4 columns and 4 rows, and let's start filling in this matrix. So for the vertex 1, we have an edge going from 1 to 2. So we will have a 1 in row 1 and column 2. Okay. Oops, sorry. Yeah, an edge going from 1 to 2. Then for the vertex 2, we have an edge going from 2 to 3. So there will be a 1 in here in row 1 and column 3. Okay. And for the vertex 3, there is an edge going to vertex 1. So we have a 1 in the 3rd row and 1st column, and there is an edge going from vertex 3 to vertex 4. So we have a 1 in 3rd row and 4th column, meaning that there is an edge going from vertex 3 to vertex 4. And there are no edges going out of vertex 4, so the 4th row is empty. Well, there are zeros. I'm not putting in zeros in this matrix. So this is the adjacency matrix for this graph. And if you want to list the edges, well, the edges are 1, 2, 2, 3, 3, 1, 3, 4. 4 edges, and hence 4 ones in the matrix. And you can also count the edges here in the graph. Well, yeah, there are 4 edges. So an example of a graph, it's adjacency matrix and it's edge list. Okay, any questions on adjacency matrices, edge lists, and representation of graphs? Well, if not, then let's go to the Dijkstra's algorithm, the algorithm for finding shortest paths in graphs. So here I'm showing the pseudocode for the algorithm. Before I continue, one question: should I switch to showing just the slides, or is it okay for you if I have this, split screen where on top I'm showing the slides and on the bottom I'm showing the Jamboard? Let me know if you want me to switch back to showing just the slides. So to understand what we will be doing, for some time we will be working here on the slide, and then we will again have an example on the Jamboard. When we have the example, of course, I will switch to this split view. But before that, I could go back to just showing the slides. But well, if you see it well, even like this, then fine. I'm fine with working with this split screen. And again, if necessary, you can just open the slides separately in your favorite application. Anyway, so Dijkstra's algorithm. As the input, we have a graph. Well, the graph is weighted. Of course, we are working with graphs where the weights represent the lengths of the edges. And in the output, we will have the length of the shortest path from node 1 to the last node in the graph. Okay. Or actually, what we will have is not only the shortest path to a single node, but we will have the shortest path to all nodes in the graph. So V is the set of nodes, and by the end of the algorithm, at the termination of the algorithm, we will know the length of the shortest path from node 1, not to just to a single node, but to all nodes in the graph. Okay, so here is the pseudocode for the algorithm, and I've taken the liberty of using, MATLAB style for comments. You don't have to do that. You can use any other style that you want for comments, but why not? MATLAB is fine. So the first part of the algorithm, this one, is the initialization. So in the initialization, you initialize the set U, and the set U will stand for unvisited nodes. Okay? So originally, all the nodes are unvisited. We haven't been in any of the nodes. We are standing in the node 1, and we just want to explore the graph, and we want to know the length of the shortest path to all the nodes. But so far, we haven't visited any node. And what we will do is that we will assign the label to every node. We will assign the label of infinity to every node in the graph. Okay, so for every node in the graph, we're saying its label is equal to infinity. Oops, sorry. Now this label, it means to represent our knowledge of the shortest path from node 1 to node V. And when we haven't seen any other nodes, we don't know what the length of the shortest path could be to any of the nodes. So we are setting up the labels which are kind of the upper bounds on the length of the shortest path to that node. And in the beginning, we can only say, well, the length of the path is smaller than infinity. Or maybe it's infinite. Maybe we will never reach a node. So this is all we can say about any node. So we set in the label of every node to be equal to infinity. But the label of node 1 will be equal to 0. Why? Because if we are standing in node 1, then we know that to get from node 1 to node 1, well, we don't have to travel at all. So the length of the shortest path from node 1 to node 1 is equal to 0. So again, in general, these labels will represent, at the termination of the algorithm, these labels will represent the length of the shortest paths from node 1 to all the nodes. And during the execution of the algorithm, these labels will give us the upper bounds on the length of the path. So we will always know that the length of the shortest path from 1 to node 5 is at most the label of node 5. And we will keep updating this label, discovering shorter and possibly shorter path to all the nodes. But in the beginning, all we know is that, well, the best upper bound we can give right now on the length of the shortest path is infinity. Of course, we know that the length of the shortest path is at most infinity, but nothing better can be said about any node except node 1. We are standing at node 1, so the length of the shortest path from node 1 to node 1 is 0. So that's the initialization. So we initialize two things, initialize the set of unvisited nodes. It is equal to all nodes in the graph, and we initialize the labels like this. Okay, any questions about the initialization? Okay, so after we have initialized the labels and the unvisited nodes, we go into this main loop, and we keep visiting nodes one by one. So until there remains an unvisited node, what do? We look at the unvisited node with the minimum label. So this thing argmin means that we are finding the node V for which the label is as small as possible. So among all unvisited nodes, we look at their labels, and we are finding the node with the smallest label, with the minimum label. So this min is the value of the label, and the argmin is the node that has this minimum label. Okay, so essentially we are looking at the unvisited nodes and finding the node with the smallest label. And yeah, I understand that maybe this notation is more complicated than how it sounds in plain language, well, whatever. Here is also some kind of explanation or comment. All we're looking for is the node with the minimum label. And what we do, well, we remove that node from U, or we visit that node. So we remove it from the set of unvisited nodes, or in other words, we visit this node. Okay. And then what we do next, we look for all unvisited nodes that have an edge from this node V that we have just removed from unvisited. So maybe here is our node V, and it is connected, to certain nodes, maybe to this one, maybe to this one, maybe some other ones. So we look at all these nodes that are connected to V, for which there is an edge from V to U, and we update their labels. And the new label is the minimum between whatever the label that you already have at that node and the label of V plus the length of the edge, VU. So at this node, maybe there is, I don't know, maybe this node 3, and maybe it has some label, L of 3. And we are comparing this label to the label of V plus the length of this edge. And we are taking the minimum. So this step is kind of called the propagation. So the node V propagates its label along all the edges adjacent to the node. Okay, so that's the algorithm description. I wouldn't expect you to fully understand and be able to follow it right now. Hopefully, with enough examples that we will do now, first in slides, then on the whiteboard or Jamboard, and then also in homework, you will get to know the algorithm better. So here is a description, and I'm not asking whether you have any questions on it or not. Maybe you do, but let's see a bit later. Here is an example, this graph, and well, it has certain weights on certain edges, and the unlabeled edges have length 1. So let's execute Dijkstra algorithm on this graph. So we are setting, first of all the nodes are unvisited. And the first thing we do is we set labels to all the nodes. Well, all the nodes, get infinite labels, except for node 1, whose label is 0. Okay, so this is the graph. So this is how the graph looks like after the initialization step. Again, I'm not showing the infinite labels, at all the nodes, not to put too much notation where it's unneeded. So any unlabeled node has infinite label, and node 1 has label 0. So this is the initialization, and all the nodes are unvisited. Okay. So that's the initialization. Let's do the main loop of the algorithm. Let's go into here and execute the algorithm. So what do we do? Well, first we want to find the node with the minimum label among the unvisited nodes. Well, all the nodes are unvisited. All the nodes have infinite labels except for node 1, which has label 0. So that's the minimum label. So what we do is we say, well, the minimum label node is node 1. And I'm showing it here with this shaded color. So node 1 becomes visited. Its label is 0. We know that. And now let's do this propagation. So for all the edges that emanate from node 1, the node which we just visited, we have to propagate the label of the node. So in particular, we look at all the nodes and we check what is smaller, the current label of the node, which was infinity, or the label of 1 plus the length of the edge from node 1 to that node. So again, let's look at node 2. Its label used to be infinity, and we are comparing this to the label of node 0, which is 0, plus the length of the edge from node 1 to 2. So this is 10, this is infinity. 10 is smaller, so the label of node 2 gets updated. Instead of infinity, it becomes 10. Okay, so that's the execution of this line. We look at the previous label of the node, which was infinity. Here it is. And we look at the label of node V, the one which has just been visited, which in this case is node 1. And we add to that label the length of the edge from V to the node 2. Well, that length is 10. And this sum is smaller than the current label. The current label is infinite. The sum is 10. 10 is smaller than infinity. So we update the label of node 2. And the new label of node 2 is 10. And similarly, we do the propagation of the label of node 1 to all the other nodes connected to node 1. So here is node 4. Its label used to be infinite, and now it's 0 plus 5, so it gets updated label 5. Node 3, it used to have an infinite label, and we compare that to 0 plus whatever the length of this edge is, 6. 6 is smaller than infinity, so here is the new label of node 3. Okay. So every time we look at all the unvisited nodes, finding the node with the smallest label, which in this case was node 1, because everybody had labels infinity, and this one had label 0. 0 is smaller than infinity. And we mark this node as visited. We remove it from the set of unvisited nodes, and we propagate the labels. So for every node to which the currently visited node is connected, we are updating the labels. We are checking what the new labels will be. Okay, that's one step of this while loop. Well, let's continue. So here is our graph after the first execution of this while loop. This node is visited, everybody else are unvisited. Which node has the smallest label out of all the unvisited nodes? Well, this has infinite label, 6, 5, 10. Between 6, 5, and 10, this node has the smallest label, so we mark it as visited. Okay, at the next step, this will be our node V, the one with the smallest label among the unvisited nodes. Its label is 5. And we have to propagate this label along all the edges that emanate from this node. Well, only one edge emanates from this node. So we do the propagation only along this edge. What is this propagation? We'll look at the head of that edge. This is node 6. It used to have infinite label, and now it can have label 5 plus the weight of this edge. The weight of this edge is 1. It's unlabeled, so the edge is unlabeled, so it has weight 1. The weight of this edge is 1, so 5 plus 1 is 6. That's the new label of this node. Okay, so this is how the graph looks like after the second time this while loop is executed. Okay, so one by one, we are looking at unvisited nodes. Among the unvisited nodes, looking for the node with the smallest label, make that node visited, update the labels of the nodes to which this node leads. So next step would be what? Okay, so looking back at this graph. So here are the unvisited nodes. Well, they have different labels. Well, two nodes have label 6. So among these two, we take the node with, let's say, with a smaller number. So we take this node, node 3. It has the smallest label. The node becomes visited. And for all the nodes that are connected to this node, we update the labels. So this is a node to which this node is connected. Its current label is 6. So this is what it is now. And we compare it to the label of this node, which is 6 plus 2. Well, 6 plus 2 is 8. So the current label of this node is 6. And the competitor is 8. Well, 6 is smaller than 8, so we do not update the label of this node. It remains equal to 6. Okay, so this is too large, so we keep this value. Okay, few more steps. Again, look at all the unvisited nodes. Well, there are 3 now. This one, and this one. 10, infinity, and 6. The smallest label is 6. So this node gets visited. It's not connected to any nodes, so there's no propagation. That's it. The loop, while loop is done. Next step, in this graph, we have 2 unvisited nodes. Node 2 has label 10. Node 5 has label infinity. So I guess node 2 is the one to become visited. Its label is 10, and we are updating the labels of the 2 nodes that are connected to node 2. Well, when we propagate along this edge, from node 2 to node 6, the label of node 2 is 10. 10 plus 3 is 13. Well, this is larger than 6, so we don't update the label of this node, node 6. And we also propagate along this edge. 10 plus 1 is 11. 11 is smaller than infinity. The label of node 5 used to be infinity. So now it becomes 11. Okay. The last unvisited node, node 5, its label is 11. It becomes visited. 11 plus 1 is 12. 12 is larger than 6. So label of node 6 is not updated. Done. All nodes are visited. While loop is finished, we have the length of the shortest path to all nodes in the graph. Okay, and now I can ask you if there are any questions. We will have another example right now on the Jamboard, just one minor note that you can view this Dijkstra algorithm as kind of wave propagation from node 1. So it's like, you know, these edges, they're grass, or maybe they're logs, and then you ignite node 1 and the fire propagates along the edges, and certain times reaches certain nodes, and when it does, we continue the propagation out of those nodes and so on. Okay, so let's have another example of Dijkstra's algorithm. So I'm going to page 3 in the Jamboard. Let's see, we have 10 minutes, so let's take a small graph. Node 1, node 2, maybe this is 5, node 3, and maybe this is 4, and maybe this is unweighted edge, so weight 1, but I'm not going to show weight 1. Okay, so this is node 4, and let's, you know what, maybe this is also 1. So maybe this is our graph. So the point is not to make the graph complicated. The point is to, you know, do the Dijkstra's algorithm. Okay, so we do the initialization. All nodes are unvisited. The set of unvisited nodes is 1 to 4. And all the labels are equal to infinity, but I'm not going to draw the infinity because, well, unlabeled node means its label is infinite. And the label of node 1 is 0. So we are done with the initialization. And let's start visiting nodes. So I claim that the first node to be visited is node 1. Well, it has the smallest label. Okay, so we remove it from the set of unvisited nodes. I should list them explicitly, 1, 2, 3, 4. And we do the propagation along the edges emanating from node 1. So the current label of node 2 is infinity, and we compare it to the label of node 1, which is 0, plus the weight of this edge, which is 5. And 5 is smaller than infinity, so the new label of node 2 becomes 5. Okay, it used to be infinity, now it decreases, it becomes 5. Similarly, for node 3, its label used to be infinity, and we are comparing it to 0, which is the label of node 1, plus 4, the length of the edge from 1 to 3. And of course, this is smaller, so the new label of node 3 is 4. Okay, so done with one step of the loop. And now we have 3 unvisited nodes, node 2, node 3, and node 4. So these guys are unvisited. And they have labels infinity, 5, and 4. And out of these 3, label 4 is the smallest one. So this node becomes visited, node number 3. And we do the propagation of its label. So from here, we go to node 4. It has the label infinity. And we compare it to 4, which is the label of node 3, plus 1, which is the length of this edge. Of course, this is smaller, so it gets label 5. Okay, done. So now, yes, and we have to remove node 3 from the set of unvisited nodes. We have visited it. So now here are the unvisited nodes. Both of them have label 5. So, okay, we can take arbitrary one, but let's take the one with the smallest, with the smaller number among 2 and 4. So let's say that node 2 is now visited, removed from the set of unvisited nodes. Its label is 5, and we now have to propagate along the edge from node 2 to node 4. Now the current label of node 4 is 5, and we have to compare it to the label of node 2, which is 5, plus the length of this edge, which is 1. So this is 6, and this is larger than the current label of node 4, so the label of node 4 stays equal to 5. Okay, next step, our one and only unvisited node is node 4, so we visit it. There are no edges emanating from it, done. So these are the labels 0, 5, 5, and 4, which give you the length of the shortest paths from node 1 to all nodes in the graph. Okay, any questions? You don't have, so I was doing everything in a single picture of the graph here on the Jamboard. In the lectures, I have several pictures of the graph. Well, I'm not sure about homework, but on the exam, I will give you several pictures of every graph so that you can, work iteration by iteration. When you do things, you don't have to do everything in a single picture. You can have several pictures of the graph and do iteration after iteration. In fact, on the exam, you will have to use one picture of the graph for each iteration so that I see how you're going through the iterations of the algorithm. All right, 4 minutes remain. Few notes. I guess the next slide will be the last slide. Yes. So some notes. Well, we may have situations where certain nodes are just unreachable from node 1, like for instance over here. Well, what do we do there? In that case, we do as many iterations as there are nodes in the graph. We know that after that many iterations, all the nodes have to be visited and labeled. Or we can watch for no changes in the labels. If you see that there are no changes, then there will be no changes later. Or we can just add infinite weight edges, to represent missing connections. So maybe all these edges that are not here, they all have weight equal to infinity. So that's one note that for disconnected graphs, Dijkstra algorithm still applies. Very often you would see that the starting node, if you look at other descriptions of Dijkstra algorithm, the starting node is S. And well, I'm using the starting node 1 because it's kind of more like things are represented in MATLAB. The nodes are just numbered from 1 to n. There are no S, A, B, and so on. But oftentimes you would see S. When you take in this label, the node with the minimum label, there could be ties, and I guess we had sometimes. In that case, you just choose the smallest node or the node with the smallest label. So, you know, if you have 3 unvisited nodes, 2, 3, and 6, and these are the labels, then, well, nodes 2 and 6 have the same label, and that label is minimum. Out of nodes 2 and 6, choose node 2. That's just a tie-breaking rule. Okay, so these are a few notes. And last but not least, in the remaining 3 minutes, I want to show you how to get the actual shortest paths. So after running Dijkstra algorithm, at least in the way I presented it, and I try to present it in the simplest possible way, you will get the labels of the nodes, that is the lengths of the shortest paths, but you will not necessarily know how the shortest paths go, right? I mean, if I just give you this, well, the labels, but how do you know, how do you get with the path of length 6 from node 1 to node 6? And to do that, you can do the backtracking and find the shortest paths from node 1 to all the nodes in the graph. In fact, those shortest paths will form a tree. And the way to find that tree is to look at every edge and see whether the difference of the labels at the endpoints of the edge is exactly equal to the length of the edge. So some examples, look at this edge. This label is 11, this label is 10. The length of this edge is 1. Hence, this edge is in the shortest path tree. Look at this edge. This label is 6, this label is 10. 6 minus 10 is not equal to 3. Hence, this edge is not in the shortest path tree. And so on. So for every edge in the graph, you check whether it is true that the label of the tail, which is 5 in this case, plus the length of the edge is equal to the label of the head. If it is the case, you include the edge in the shortest path tree. If it is not the case, you do not include it. And the edges which are included in the shortest path tree will give a shortest path to all nodes in the graph. Well, that's what we need.